Very much. Hello, everybody. First, I want to thank all the organizers for inviting me to this very fascinating and beautiful program and giving me the opportunity to speak to you today. So I'm going to talk about single-species, non-reciprocal spin systems. And yeah, this work that I'm the main part of the work that I'm presenting is together with Mike Cates and Noah Grodzimski, who is a master student that I've been supervising, and the main part has actually been done by Thomas Suchanek, who is a very brilliant PhD student that I have the pleasure to supervise. So I want to acknowledge that. And then some other part is also done together with Sabine Klapp from TU Berlin and Thomas Martinek from TU Berlin. And yeah, what I want to say is that the main part of my talk is actually a very ongoing work, so I'm very grateful for any kinds of comments, suggestions, and ideas and questions from your side. So Rio already gave a very nice introduction to non-reciprocity, so I don't have to say much. Just to remind you that the fact that action-reaction symmetry is broken on the microscale of course implies directly some other kinds of symmetry breaking, such as broken momentum conservation, which is very easy to see from such a sketch where you have a run-and-chase interaction, which would introduce a transient flow in the system. And, but this also leads to broken time reversal symmetry immediately, because you have the notion of a chaser which breaks time reversal symmetry. However, just because these symmetries are broken on the microscale, it doesn't necessarily mean anything for the macroscale. So if I take a lot of these particles, put them in a box, and look from far away, I wouldn't necessarily see that this is an out of equilibrium system. So it's a very interesting and non-trivial question to study how non-reciprocity shows up at the collective level, whether it gives rise to new phase transitions. And what personally interests me also is that to what extent this can be a mechanism to bring an error of time that you have on the microscale actually to the macroscale and introduce macroscopic irreversible behavior. Yeah, and these questions have, of course, already been studied quite a bit in the last years. And in this very audience are some of the leading figures in this research line. So I don't want to present their work to themselves, but just to show some of the beautiful pictures and videos which make, I think, really apparent that non-reciprocity can easily give rise to dynamical phases that are marked by macroscopic transport or macroscopic flow. And of course also new transition scenarios, as Rio has already explained nicely, such as these critical exceptional points that are quite ubiquitous and are often responsible for these dynamical phases. But that's, of course, also not the only phase transition scenario that you can get due to non-reciprocity. Yeah, we have also looked a little bit at this and studied the fluctuations close to such critical exceptional points and the irreversibility. But this is not going to be the topic of the talk today. I want to look at this from a different perspective. So all of these very different and rich models have a common feature, and that is that the non-reciprocity is introduced in the form of interactions between two species. And this is a very clever way of doing it, because then within the species you still have kind of normal statistical physics, and you can use that to make quite some progress. But I would argue that this is not always possible, and there are many interesting systems in nature and synthetic systems where you cannot make this distinction and where you have a single species kind of system. So social dynamics is a good example, or also these levitating nanoparticles that are realized in recent experiments. And I would also think that in many active fluids and active solids, this is the case. So that should motivate it while we look at this. But I think for the kind of systems that system that I'm going to present, the best motivation is to think about a neural system, either a biological or a synthetic or a machine learning algorithm or something where you have also non-reciprocity. And as you can already see from this sketch, there will be disorder in these systems. So I'm going to talk about this kind of problem. And finally, I want to say one other conceptual thing that I like to think about, and that's the notion of energy in non-reciprocal systems. So if you have non-reciprocal interactions, clearly you lose the notion of global energy minimization, but you can still think about local energies. So each component can still have local energy, but why it's out of equilibrium is because a move that lowers the energy of one particle would increase the energy of the other particle. And if we think about this run and chase, this gives it an energy picture that reminded me a little bit of a Penrose staircase, because while these particles chase each other, actually both particles think that they slide along a potential downwards, but they just do that forever. So I just found this is a nice analogy. I don't know, it's deeper than that. But yeah, I want to think about to what extent an energy picture can still be useful for non-reciprocal systems. And I'm addressing this using a kind of combination of statistical mechanics and dynamic field systems perspectives. So how can you introduce non-reciprocity in a single species system? One thing that we explored in the past is if you have interactions that are mediated by sensing, and the sensing is sort of anisotropic, such as visual perception that naturally gives rise to non-reciprocity. This bird would not react to its neighbor, but this bird would react to its neighbor. So we wanted to see what kind of physics you get from that. So we take the classical XY model and we modified it in the way that we just introduced vision cones. So we give a local energy that looks very similar to the usual one, but now the coupling would depend on the instantaneous system state. And if your neighbor doesn't lie within your current vision cone, you just set the coupling to 0. You can still define a local energy, so you can also run something like a Glauber-like dynamics. And this is what we have done. And with that, we computed this phase diagram for this model. So this is in 2 dimensions on hexagonal lattice. And this is the temperature, and this is the vision cone. And for the temperature, if the vision cone is 360, this is the classical XY model. And so you would expect that you have a disorder and a quasi-long-range ordered phase, and no long-range order due to Mermin-Wagner. And then what we found is that if you introduce this vision cone, and even you just cut out like a very small fraction in the back, so it's almost 360 degrees, you get a long-range ordered phase. So the vision cone doesn't act like a small perturbation here at all. And the reason why you get long-range order can be explained by the suppression of spin waves. And also the transition scenario, so the order of the phase transition will now depend on the lattice geometry. And what we also found is that the irreversibility in such a system is then only apparent on the level of fluctuations, because such a phase diagram you could also in principle get in equilibrium. Okay, but I think I don't want to talk more about this model. I'm very happy to discuss this. If people have questions, I also have some backup slides, so feel free to ask about it. But I want to come to the model that we are studying currently. So the other way I could think of how to introduce non-reciprocity in a single species model would be by introducing quench disorder, by randomly just setting some interactions to a non-reciprocal value. And that is inspired by neural systems, as I said. Okay, so now we look at an XY model where the interactions are chosen from some random distribution. We also look at different topologies, so we vary the adjacency, and we are interested how the random distribution that you choose here affects what kind of phases you get. And clearly, by setting this and freezing this in time, you introduce quenched disorder in the system. So in a sense, this system becomes similar to spin glass models and also the Hopfield model with weak asymmetry that has been already studied quite a bit starting from the 80s. But we are here interested in a different question, I guess, and also the way we are going to introduce the quench disorder is different from these models, but I think there are probably more connections that we still need to understand better. And as I'm sure there are people here who know much more about it, I'm very happy to learn from you. A variant of this model has also been studied by Rio in his very nice recent PRX paper, where he showed that if you have a spin chain and you choose a Gaussian type of coupling distribution, the system generically develops a glassy-like dynamics. And he also established this analogy between this non-reciprocal frustration and magnetic frustration. So yeah, let's look at the example of just two spins to get an idea of what's going on. So if I have two spins and I give them a non-reciprocal interaction but with the same sign, then what will happen is that the spins will still be able to agree on a common state, either ferromagnetic or antiferromagnetic, and this is also because their local minima, energy minima actually align. So they are both happy and nothing happens. If I introduce non-reciprocity in the way that they don't agree, so one is attracted, the other one is repelled, but with a different intensity, then they can still agree on something because the one that is just more passionate about their relation will win, and yeah, they still fall into a sort of attractor, and now the minimum of the spin with the stronger coupling acts as the attractor of this dynamical system. And then the special case that the interactions are anti-reciprocal with the exact same magnitude leads to a scenario where they will run and chase forever, and you have these degenerate orbits where the orbit is selected by the initial condition that they can never get rid of, and the angular velocity depends on the difference of their phases. And in this particular situation, the total energy is actually conserved of the system, which, I mean, the total energy doesn't really play a role, but I still find it interesting because this is very reminiscent now of a Hamiltonian system, where also the energy is conserved, and you would also have these degenerate orbits, right? So, and of course, here we are in a different situation because here we have dissipation. So that's not trivial that you get there. Okay, so now we don't just look at two, but we look at a bunch of spins, and we were interested in the question, what happens if I just inject a few of these non-reciprocal links? So the kind of random distribution that we are going to look at is chosen in a bimodal fashion, so all the coupling intensities have the same magnitude, but different signs. And the only relevant parameter now is P, which gives us the fraction of the non-reciprocal links. And we will vary the nature of the other interactions. And this bimodal distribution has some nice properties. So the total sum over all the angular momenta actually is only determined by the non-reciprocal links, and the total energy is only determined by the reciprocal links. And this is very useful for us to make some analytical progress in the system. Okay, so we start with a ferromagnetic system where we just inject a few non-reciprocal links. So this system has a global energy minimum without the non-reciprocal links, and we perturb this now a little bit and want to see what happens. So what we find is that the system can express two different states. It can either give you a static state, so the normal ground state where everybody is ferromagnetically aligned, or it will sometimes also express a dynamical state where this looks like a self-generated noise and the system never comes to a rest and will just continue to do this motion forever. And we calculate the maximum Lyapunov exponent and see that this is a chaotic system. And the way to think about it is that you have a lot of oscillators here and they have incommensurate frequencies. So this system is very susceptible to develop chaos. On a lattice, we actually find that only the chaotic state is expressed as soon as you introduce a little bit of non-reciprocity, actually even a single non-reciprocal link. If you go to the all-to-all case, then the system becomes sort of bistable. So whether the dynamical or the static state is expressed depends on the realization of the random disorder. And what we also find is that for n to infinity, you only get the chaotic phase for really p equals 1. So if half of them. Yes?
Can you get chaos with just 3 spins in an equilateral triangle with non-reciprocity?
No, that would not be chaotic. So then you would have these marginal orbits, and they would not intersect, and this would not be chaotic.
So tetrahedron?
Yes, yeah.
You can get it.
Yeah.
Thank you.
Yeah, thank you. Okay, and the reason why I think that you don't get a chaotic state for this all-to-all coupled system is that we have the combination of these non-reciprocal links with this global energy minimum, which sort of pushes them together so that they all end up aligned and then they stop moving. So for n to infinity, only the case p equals 1 will become chaotic. And what happens at this point is that you have 50% ferromagnetic and 50% antiferromagnetic bonds. Of course, because clearly the way we introduce non-reciprocity also introduced at the same time disorder and magnetic frustration. So we want to study better the effect of these. So now we start with a system that already has these features. So at even without non-reciprocity, we look at the system that has 50% ferromagnetic and 50% antiferromagnetic bonds. So this is a magnetically frustrated system, which has a shallow and degenerate energy landscape with lots of local minima and marginally stable directions. And then we introduce the non-reciprocity. And I think, to no surprise, this would have a huge effect because the system is very susceptible to any kind of perturbation. And indeed, what we find is that the static state is immediately gone. You have no static phase anymore, and this is even true for a single non-reciprocal bond on all the lattice geometries. So the question was, does this just lead to chaos? First, we look again at the lattice. This is a 2D square lattice, and again, we find that there's only a chaotic state and no other phases. So this is very much like the ferromagnetic case. So in this sense, so on the lattice, where you have this local couplings, it actually doesn't really play a role what the global ground state was. Now, we looked at the system on the all-to-all coupling topology, and we find that there's again sort of bistability, and depending on the realization of the random disorder, the system chooses either to go to this chaotic state. Here, by the way, I'm showing the phases, and these are the angular velocities. And at time 0, the system was prepared such, so at time 0, the system was relaxed without the non-reciprocity, and then we switched them on. So that's why you have like a uniform distribution of all the phases. Yeah, and in addition to this chaotic state, we also find this synchronized disordered state, where the system all gets a homogeneous angular velocity that is really, really sharp, and the spins move together. So the system collectively turns.
Sorry, a question. You get that for a different parameter value, or just same, or are they coexistent?
Yeah, so let me, I think it's on the next, so here. So this is the probability to get the chaotic state.
Yeah.
And we do it such that we change the realization of the random disorder, and then we run lots of initial conditions. And we count it as chaotic only if we only see the chaotic phase.
Nice.
Because we think that maybe if we sometimes see the other one, then this is an attractor that we eventually will fall into. And here you see the probability. So if you increase p, it gets more likely to go to the chaotic state, and eventually you will only go to it. But for small p, you're always in the synchronous.
So p is the fraction of disorder.
Yeah, the fraction of the non-reciprocity. Disorder is always same. Yeah. And then what you can also see is that for n to infinity, only the chaotic state survives. So this synchronous solution is only in finite size systems. Yeah, thank you. Yeah. Okay, yeah, and not all properties depend on the system size though. So for example, if we look at the mean squared velocity of all the spins, then we find that it scales independently of the system size, and it only depends on the fraction of non-reciprocity, and this is true in the chaotic as well as in the synchronous state. But for example, the variance of this squared velocity, that scales with the system size. So if we make it bigger, it gets more and more chaotic and disordered. Yeah, so how can we understand this coexistence of chaotic and synchronous states? So you could think about it that maybe in the phase space, so this is just a sketch, there is some chaotic attractor and there are some stable limit cycles and maybe they do coexist. But yeah, it's hard to say. For this value p equals 1, again, I want to recall that there we have these marginal orbits for small systems. And indeed, as Rio has shown, that in this case, the phase space volume actually cannot contract. So the total energy is conserved. You pour in the exact same amount of energy that is being dissipated at all times. So you can actually not contract to any attractor. So you're always kind of on the ground state manifold from the beginning. But it doesn't really seems to play a crucial role for the dynamics of these finite dimensional systems. Yeah, and then again on the lattice. No, sorry. Again, let me compare what we have found so far. So the static to dynamic transition occurs in this random disordered system already at 0. So you need only a single bond and you will destroy the static state. And the transition to chaos on the all-to-all coupled system happens at some critical value of p. I mean, critical is maybe an exaggeration. At some value of p, that in the thermodynamic limit goes to 0, while on the lattice, you have chaos for any value of p. So we wanted to understand the difference, why you sometimes have this temporal order for the all-to-all case, and why you have this temporal disorder, the chaos case, for the finite dimensional system. And a clue to understand this is to look at the spectrum of the unperturbed Jacobian. So now we look at the unperturbed Jacobian. So we look at the unperturbed Jacobian, which is just with respect to the reciprocal system, and we consider the non-reciprocal part as a perturbation to that. And we look at the set of all the largest eigenvalues of all the stable fixed points of the Jacobian of this reciprocal system. And importantly, we just look at the orthogonal component to the Goldstone node. So what will that tell us? So the maximum value of this will give us the least stable direction, so the loosest spring of the least stable local minimum. And the minimum value will give us the least stable direction of the most stable fixed point. So assuming that the system runs into the most stable fixed point, this minimum value here is the important one. And then with the non-reciprocal bonds, we actually excite the system. So it's a bit like adding noise, and then you would expect that these perturbations play a role in the least stable direction. And what we find is that on the infinite dimensional system, there's a kind of gap, and the system always has a stable direction here. While on the with the finite dimensional system, if you increase n, this minimum value actually here converges to 0. And what does it tell us? Oh, yeah, sorry.
Just a question, with these non-reciprocal systems, I would have thought you would get complex eigenvalues if you minimize.
Yeah, that's true.
So are you talking about the real part?
Yeah, so here I'm talking about the real part, but it's true that in general they could become complex. But we actually...
What does the spectrum look like in the complex plane?
We haven't studied that. Yeah.
That might be interesting.
Yeah, it's a good point. Yeah, we should study that in more detail. Yeah, but we found that in the regime where you have only a small perturbation, they're actually still real. So, but yeah, and we haven't studied this full spectrum. I think that's something we need to do. Yeah, but so the argument, I just want to finish this, is that this indicates that the infinite dimensional system is sort of rigid, while the finite dimensional system becomes soft. And then if you add on top of that the fact that this perturbation here is a non-Hermitian operator, so they can actually couple. It means that you can also, this dynamics actually couples to the Goldstone mode. So what happens here is that you have a rigid system that is sort of excited and coupled to the Goldstone mode, and that means you can globally rotate it. While here you have a soft system, and it's also soft because of spin waves, by the way. And when you want to perturb that, you actually will just locally perturb it, and you cannot get this synchronous solution. And this picture fits very well to what we actually see, right? So the disorder is actually conserved, and you have sort of every fixed point of the system turns into a limit cycle and starts to turn around its Goldstone mode. Yeah, so you keep the disorder of the local minimum, but you just globally rotate it. So we believe that this is what happens here. And we want to make this more rigorous, so and we can do this by using a sort of expansion of similar to a quantum mechanical perturbation theory, now with non-Hermitian operators. But this is still a work in progress, so I don't want to show anything because who knows. But yeah, and then finally, I just want to say that so far we have kind of studied the system by looking at the unperturbed system and then perturb it around that. But we can also go from the other direction and think about the system of coupled oscillators with random frequencies and try to understand the dynamics coming from that direction. And indeed, for this value p equals 1, we find that the oscillators are sort of uncorrelated. So what we can do is kind of making a self-consistency approach where we say that the noise that each individual spin receives must be the same that the noise that this gives to its environment. So it has to produce the same kind of dynamics that it receives. And with such an ansatz, we can, not exactly calculate, but we can get a quite good approximation of the statistics and the correlations in this system. And again, this is also something we want to make more rigorous, which we could in principle do by a dynamical mean field theory, although because this is a non-Gaussian system, it's not straightforward, but there's a very nice paper that had recently generalized dynamical mean field theory to non-Gaussian systems. So we hope that we can do this at some point, if I'm able to. Okay, so with this, I want to finish. I hope I could convince you that these kind of systems are sort of interesting to look at. I'm very happy about suggestions and comments. As I said, also, I will be here quite some time, so maybe you can help me with your insights. And I'm happy to take kind of questions now.
All right, thank you very much, Sarah. We got the first question over there.
Hi, thanks for the nice talk. I'm not sure if I understood exactly. I had the impression that all your equations were deterministic.
Yes.
Okay. And I have two questions. What is the motivation for looking at the deterministic limit? Mm-hmm. And do you know what happens when you add noise?
Yeah, it's a good point. So initially we started with a noisy case, actually. But then I was not satisfied by that because we realized that there is kind of chaos and thermal noise. So they kind of overlap with each other. And so this was the motivation then to study the deterministic limit first and to really understand what's going on in the...
But in this case, do you know what happened with the bistability, for instance, that you were discussing? You were saying that you have initial condition and then sometimes you get to the attractor, sometimes not.
Yes, so we have studied, we haven't really studied that systematically. So the synchronized state we actually only discovered by accident in the simulations. We first thought it's a bug, and this was for very low noise. So I don't know if this would survive if you add a lot of noise. It's that's definitely something we want to study. In some sense, it can also help us if we want to calculate things. But I felt like because we already have a sort of disorder in the system that we put in by hand first, so we have this noise in the couplings. I didn't want to do thermal noise, which is very unusual for me because usually I only study noise. But as I said, I kind of also like the idea that you can study the chaos as a kind of self-generated noise. So I want to understand a little bit the properties of that. So what we are also doing is to study the spectrum and so on, that the self-generated noise is adding. And I think maybe the fact that you have kind of self-generated noise is also more general to non-reciprocal systems. So you could imagine that you have that in other kinds of non-reciprocal systems as well. So I wanted to study that. Thank you.
Since you have that slide up, so in the neural networks literature where people have also looked at the effects of asymmetry in the interactions, there is a special case where the interaction matrix is fully asymmetric, so there's no off-diagonal, no correlations between Ji and Ji. And in that case, also the reduced dynamics for the single degrees of freedom becomes Markovian. So you lose the contribution on the response function. So you think that's related to the fact that you have an effective sort of Markovian noise description here?
Yeah, that's a very good point. So thank you for that. I haven't thought about this, so I'm not aware of this result. So I'm very interested in that. I do think that this is a special situation here, also in our model, p equals 1, because then we also only have this anti-reciprocal interaction. So we have a purely asymmetric coupling. So I think this is probably very close to related to that. I don't think the noise is purely.
Sorry, I was incorrect in what I said. What drops out is the memory term in the equation of motion.
Ah,
so
okay.
Noise,
Yeah.
Because normally you would get a non-Markovian memory term in the single.
Yeah. Okay. Yeah. So that could be the case here too. The noise, I think, is colored, so I don't think we have a Markovian noise. So I mean, if you just look at the power spectrum, you see that it's colored. And this is also indicated sort of by the pics that we get here. Yeah.
And Christian,
so have you looked at the dependence on dimensionality? So essentially you're looking at 2 dimensions, infinite dimension. I think your simulations, you could run it in 3 or even 4 or 5 dimensions.
Yeah, we could. So I think, we also looked at the one-dimensional case. And then we got a bit lazy because we feel that the arguments that we have, it will actually not depend so much on the dimensionality. So we think that everything until infinite is more or less the same, and then you go to infinite, and that there is the difference. But this is a conjecture at this point.
The model has properties in 2 dimensions that are not equal in 3 dimensions. I would think that something could change in 3 dimensions, but.
Yeah, in general, of course, if you look at other properties, but this emergence of chaos, we have the impression that it doesn't really depend, and that also like when we look at our calculations, it seems like you only have to distinguish infinite to finite, but it's still work in progress. So
another quick comment: you could also add a few long-range connections, and that could also be interesting.
Yeah, that's something. I'm not sure if I put it on the last slide. I wanted to put a question. Yeah. So, is there any topology where the transition to chaos occurs at a finite value of a fraction of non-reciprocal links in the thermodynamic limit? And I think this could maybe be a way to sort of go in between finite and infinite dimensional by adding like a small world network or something by looking at these kind of topologies. But yeah, we haven't done that. So yeah, that's actually something I would be very happy about, because it's kind of unsatisfactory if your transitions all happen at your limits, right? So they either happen at 0 or 1. We're kind of hoping that we find a case where it's kind of a finite fraction. So yeah, thank you.
Solka?
I may be seeing patterns, but this looks a little bit like what you see with the actuation systems, where they're not formally non-reciprocal in the same way, but the emergence of the spin wave out of chaos. Do you think there's any connections?
Establishing a real precise connection is not obvious to me at all. But indeed, that's also what I kind of said earlier, that in various non-reciprocal systems, I thought, okay, there could be some sort of chaos or self-generated noise emerging. That was definitely one of the motivations to study this, but then it may really depend on the details of the system. So I would be happy to see any analogy or connection, but I'm not confident to say something.
Yeah, fair enough, yeah.
Yeah, thank you.
Sharam, I think you're next.
About this self-generated, chaos as self-generated noise, if you look at non-reciprocal Heisenberg models, classical, in which the non-reciprocality is in the precession term, those models in one limit, in the fully anti-reciprocal limit, become a Hamiltonian system.
Yeah.
So the chaos there, in fact, is the actual thermalization of that Hamiltonian system.
Yes. I see.
So in general, the fact that the moment you take what used to be a damping coefficient and introduce an antisymmetric bit, you're introducing something, a bit of symplectic dynamics into the thing. So a lot of this, the chaos is similar to Hamiltonian chaos, and so you should take a look at our paper.
Okay, yeah, I will definitely, and I will.
Sorry.
I will bother you again for the precise references. But yeah, I think, this could be well related because, as I said, also in our case, for the fully anti-reciprocal case, we have this kind of conservation of phase space, so it becomes so similar to a Hamiltonian system. So I could easily imagine that there's a connection, yeah.
Antonio?
Yes, I hesitated a lot in my mind before asking this question, and I decided to ask it. So let me so I'm not an insider, so I'm here at this conference to learn. Okay, so I will ask a question as a passerby. Okay?
That's the hardest question. So
No, I know. So, okay, so imagine, I have to teach people to build robots, okay? That's my job, okay? And okay, I accept this idea of having equations of motion in which there is non-reciprocity, okay? But, of course, my mind goes to principles like conservation of linear momentum, etc. Now, the reason in many of these cases, energy is very important, and certain effects, like self-oscillatory systems, require an energy injection in the system. So, right. And I'm asking now the question because you mentioned energy in your talk a lot, but there is no equation for the balance, for the conservation of energy.
Yeah.
So why is that? Is it trivial, or is it?
No, it's a good point. I think actually on this slide I have a statement about that. So you can of course also study the actual energy that you have to inject to realize this motion, and you can also study the actual dissipation, and then you will see that realizing non-reciprocity always requires work input, right? So because of this momentum conservation, etc. And you can quantify that, and then you can also look at the heat dissipation that is associated with this non-reciprocity. And if you sum over all these local energies, you actually see that this is a thermodynamic consistent description. But of course, for this, if you just look at a single local system, there would be an energy injection term and a dissipation term. But yeah, I think the way I did it here was also a bit provocative. That was also my intention to say, like, how much does it actually give us to think about energies in this setting? And I think in this project, I feel like it does help us to develop an intuition, although it's not strictly speaking.
Thank you very much for the answer, because it was so clear that I can ask a supplement of the question if I may. So if I now use the example of the cone of vision, okay, now what's the energy injection in that system? So should I use the formalism to understand, okay, I could describe more mechanistically the cone of vision and saying that there is light propagation, there is a photoreceptor, there's a chemical reaction, and a muscle does something, and here is the energy.
Yeah.
Okay, so should I use the formalism in this way, like trying to understand what is the energy required by this mechanism, or okay?
Yeah, okay. Yeah, so if you really want to know the actual work that you need to put in, you need to study all of that, which is going to be very complicated, right? But of course, fundamentally, there is no non-reciprocity. There is also no noise in this, at least not in the classical dynamics. So everything we look at is at the effective level. So that's definitely true for sure. So if you want to look at the real energy that you really need to do to supply, so how much energy you need to inject, then you would need to model all of that. Here we look sort of at the fundamental thermodynamic limit. If you're following a completely idealized setting, what would be the minimum energy injection that you need to do? And that is, of course, well below what you actually would need to do in reality. So it depends. If you really want to build a robot, you would maybe not care too much about this. But but of course, this is also true for any active matter system, not just for the non-reciprocal. Yeah. Okay, thank you.
Thank you for the great talk, Sarah. First, one comment. I think one experimental system that we see very similar, let's say, phenomena of this coexistence between chaos and some like limit cycle-ish behavior is laboratory microcosms, where you have enough, let's say, random interactions between these species. Then we indeed experimentally see all these different phases, and we were trying to understand like what is the determining, let's say, factor for this, let's say, whether some system would go to chaos versus this limit cycle.
Okay.
So I think your intuition about this, let's say, rigid versus also like the rigid idea was also very inspiring, and thinking about this mean and max eigenvalues. So there was a comment. And in terms of question, how can we understand better about this, the direction of the rotation that is chosen by the system?
Sorry,
is
what?
it direction of the rotation in the rigid case?
Yeah.
Is it really determined by the, let's say, the initial condition, or is it something more deeper in terms of, let's say,
Yes.
the lowest eigenmode?
Yeah, so first, thank you for the comment. I'm obviously very interested in learning about this experimental system, which I don't know anything about. And the other question, yeah, so this state, yeah, so this state where we kind of keep the disorder and then we globally rotate it around the gallstone mode, the direction is mainly chosen actually by the random disorder. So it's, it doesn't appear to be like a spontaneous symmetry breaking, but it also depends a little bit on the initial conditions. So it's a bit tricky to answer this question for me. So there is no, yeah, so I think here on the slide I had a, yeah, so this is showing the histogram actually of the velocities that we get, and you see that you can have both values depending on the random disorder. Yeah, thank you.
All right, thank you.
Thank you. And our last question.
That's a very short question. Does the spectrum of chaotic fluctuations depend on the system size? Does it approach some kind of asymptotically as you?
So, sorry, the what?
Does the spectrum of chaotic fluctuations, the power spectrum, does
yeah.
that depend on the system size?
Yes, so the power spectrum, I need to think because I don't remember if we have studied that already, or I think we have, but I forgot the answer. So I'm not sure, I have to look it up. I think I don't think it depends much on the, no, you asked about the system size. No, it does depend on the system size. So wait, I had one dot here. Yeah, so if you look at the variance of the mean squared velocity, you see that it actually scales with the system size. So the bigger the system is, the variance actually blows up, so it becomes more and more chaotic and disordered, and you reach higher velocities. Yeah, so that depends. And by the way, this peculiar dependency on P here is something we could not show. I mean, this is analytical. This is just a fit to the numerics. We don't know why P is. But it seems very robust. We have tested this quite a bit, so I don't know. The N dependence we can infer, but the P dependence, I don't know.
All right. Thank you very much, Sarah. So we will now have a half-hour break, I believe, in the courtyard, and we'll resume here at 11 with 2 more talks in our morning session. Thank you.